So let's look at some examples of subspaces from what we've looked at. Okay. All right, I'm going to define H to be the set of vectors in Rn where x1 is 0. All right. This is a subspace. Because if I look at it, if I have x and y are two vectors in H, then x is going to look like 0, x2 down to xn. Y is equal to 0, x2 down to, or y2 down to yn. If I take x plus y, this is going to be 0 plus 0, x2 plus y2, all the way down to xn plus yn. That's still in my set H because the first component is still 0. Okay. Similarly, if I take alpha times x, this is going to be alpha times 0 is 0, alpha x2 down to alpha xn. That's still in H. And the 0 vector is still in this set, okay? Because the 0 vector is just all zeros. So hooray. Sorry, I apologize. Okay, let's take a look at, are there any questions about this one? No? Okay. I'm going to look at the set of diagonal 2x2 matrices. These are matrices of the form A, 0, 0, D, where A and D are real numbers. Okay. This 2x2 matrix diagonals is a subset of the 2x2 matrices. Okay. And it's a subspace. If I take two matrices that are diagonal, I can write A as A1, A2 on the main diagonal, B as B1, B2 on the diagonal, A plus B, since I define everything component-wise, everything's fine. This is still in my set D. And of course, if I take alpha times A, it's going to give me alpha times A in the first component. A, 1, 0, 0, and alpha A2 in the second non-zero component. That's still diagonal. Okay. So that's a subspace of the 2x2 matrices. All right, so if I think about V as a vector space, H is just the set with the 0 vector in it. That is a subspace of my vector space. It's a very boring one, but it's there. So in fact, one could say this is the smallest subspace of a vector space. Is this 0 space, 0 subspace. All right. I can think about this. My space of polynomials of degree n is a subspace of the continuous functions on A to B. In fact, the set of all polynomials is a subspace of this continuous function on A to B. And there's an important theorem here in real analysis that says that the polynomials are actually dense in that space. You'll talk about that a little bit later. Don't want to steal Dr. Sterner's thunder. Okay, so geometrically, what you can think about this as, think about this in terms of Euclidean space, all right? The requirement here is that whatever plane that you're looking at for your subspace goes through the origin. Okay? The origin has to be in whatever set you're talking about in order for it to be a subspace. So if you have a plane in R3, that plane does not go through the origin. That plane does not represent a subspace of R3.